Thanks, Alistair. That's very kind. I'm really pleased to be here, and thanks for the chance to present some of this work. Yeah. As Alistair kindly says, so I'm based at the University of Nottingham. As sort of full disclosure, I am the National Professional Advisor for Patient Safety at the Care Quality Commission. Though that's not the capacity I'm speaking in today. I should clarify that connection. Yeah, my background is very much focused on patient safety and safety in healthcare the past year, but also prior to that in other sectors, mainly aviation and industries that use high levels of automation in very safety critical settings, and I still keep work ongoing in those areas, and I'm hoping that I can demonstrate what we can learn from some of the insights from at least one of those sectors, if not in terms of how to implement and manage safe AI, but perhaps how not to implement and manage safe AI, and I will say a bit more about that in just a moment. As you'll all be, more than familiar, when 5, 6, 7 years ago, when a lot of this work was starting to emerge into the public consciousness, but very few systems had been actively deployed in healthcare. That's now starting to be a very different picture. Of course, when you deploy complex technologies like AI, even in seemingly relatively simple settings, bad things can happen, and things can start to go wrong in ways you didn't necessarily expect. There's these seem almost quaint examples now from a few years back, but the clear instances, even with consumer-oriented AI, like these robot delivery. Pizza delivery robots, which you see sort of beating around in Berkeley and places on US campuses. Well, one which had a problem interpreting and getting up the curb of a pavement of a sidewalk and trapped a wheelchair user in a busy intersection. Instances of Alexa suggesting extremely hazardous games to young children when they've asked for suggestions, essentially this is to be expected with any new technology. Place it in a complex technology in a complex setting, and unexpected things happen and can go wrong. The added challenge and well, I think considerable challenge in healthcare is that we're in a situation where that there are already an enormous number of patient safety issues and complications and complexities in our health system, and these range from the minor to the deeply troublesome. Of course, everything from the infusion pumps that a typical hospital trust might use, sort of 10 or 15 different types. We still haven't yet decided whether we want the one on the keypad at the top, like a mobile phone, or perhaps at the bottom, like a calculator. Just very basic human factors, sort of insults that we provide to our clinicians daily. We know that the reliability of a lot of clinical processes and systems effectively often runs at around about 80% reliability. So things like do operations do operations begin with all the correct equipment, with no equipment problems? Are outpatient appointments conducted with all the information that's required? And the research that's been done in this space indicates that these processes are not hugely reliable. In fact, Roger Rezar of the Institute for Healthcare Improvement over in the US actually calls this level of reliability essentially chaotic processes, and perhaps it's a stretch to call some of these a process if it's only working 4 times out of 5. Likewise, for the final piece of bad news here is I think the challenge of actually understanding and identifying and analysing and improving these sorts of issues is often a challenge, given that the national report, well, the NHS England Safety Incident Reporting System, which has been running for almost 20 years now, in a study by Guy Martin and colleagues from 2004 to 2016, that analysed almost 14 million incident reports, only about just over 2,500 of them related to health, IT, health technologies. So we're just not getting a routine, rigorous insight into how a lot of technologies are being used in practice in organizational and clinical settings, from this side of our governance and oversight processes. So the question that I suppose really motivates me is how can we manage the safe implementation, integration, and use of these complex new intelligent technologies into systems that are already hugely socially and technically complex. And it's I think it's a big challenge, and inherently, and perhaps as a organizational psychologist, I would say this, but I think it's that these are deeply socio-technical challenges. That they're about they're not just about the device and human interaction with the device, but the social structures that surround and support how devices are used, the cultural context and the norms, the organizational systems and the resources and the governance systems, and all of this entire socio-technical infrastructure that needs to surround and support the safety of these technologies. We need to better understand and to better to build more effectively. And I think what I want to unpack over the next 10 minutes is actually, to do this, it can be very helpful to understand what we're trying to avoid in terms of these socio-technical risks and challenges. We've got a bit of a head start because there's half a century of work that's been done in this field across the social sciences, going back to I think the really definitive work in the 1970s, but Barry Turner, who explored the essentially how cultural understandings of technologies and their risks can become disjunct, or as he described it, sort of disjointed from the actual real nature of those risks. What he called the sort of accident etiology of how the accidents and disasters incubate in organizations as slowly risks accumulate. You have classics like Charles Perrow, who described and explored the social and the technical structures which enable disasters and accidents often to sometimes be effectively normal in his sort of definitive account of, as he called, normal accidents. So some structures and some structural arrangements simply produce accidents by way of the way that they're structured and operated. All the way through to things like Diane Vaughan's deep exploration of the decisions around the Challenger, NASA Challenger shuttle, and how cultural norms around what's acceptable in the way safety is managed and complex technologies are operated, how norms can gradually deviate, and that deviation is normalized over time. And there's essentially an enormous volume of insight and analysis that's being conducted, but very little of it actually has come too deeply into contact with healthcare. I think, and I think it's reasonable to say that, having worked in this field for so long. But I think we still have an enormous opportunity, particularly think about these complex AI technologies, to draw on a lot of the insights from these fields. So the question is, or my proposition rather, is that I think to responsibly implement and manage safe AI, we really need to understand what we're trying to avoid in terms of deployment going wrong and implementation going wrong and use going wrong. So what I want to describe is actually some lessons from another sector, and what was the world's first self-driving car fatality, which occurred 5 years ago now. This was Uber's Advanced Technology Group, ATG, a unit that's since been shut down in part because of this event. And in March 2018, one of their autonomous test vehicles or developmental vehicles crashed into and killed a pedestrian, Elaine Hertz, who was tragically the first pedestrian to be fatally injured by an autonomous vehicle. Elaine Hertzberger was pushing a bicycle which had various bags and things hung off it across the street. This was around 10 o'clock at night, and essentially what happened was the test vehicle failed to recognise and respond appropriately. Just to give you a sort of brief summary of this, because I think it's useful for us to excuse me, reflect onto our own experiences and technologies in healthcare. Essentially, these self-driving systems collate a huge amount of data from a variety of different sensors, and try and identify and categorize different objects, track and predict their past and future paths, what their assumed goals are, and then feed that all into a sort of complex motion planning system to decide what to do next. But essentially, this is a system which is taking thousands and thousands of images every minute and trying to classify and predict. Make predictions from those images, and if the system gets it wrong, then it's within seconds literally within seconds of causing fatal harm to a human. So this is a real sort of crucible of where these AI systems are being implemented in public arenas. What happened in this instance? The system failed to effectively classify the pedestrian. It cycled through first a vehicle, then other, then bicycle, 1.2 seconds before the collision. When the object when an object was reclassified, the system lost its historical path data, so it started again in terms of trying to predict where that particular object would go. It assumed it was almost a new object effectively. Likewise, no goals were assigned to certain types of object like other, which were just assumed to be a stationary object, or rather oddly, pedestrians in the road were not assigned a goal in the system. They were just assumed, presumably, to be in the road for some reason, and were their motion was predicted based on their continuous tracking, which of course was in this case lost because of the struggle to classify Elaine as a pedestrian. Now, 1.2 seconds before the collision, the bicycle was determined to be an emergency situation, but there was an action suppression system which delayed any response from the system for 1 second. This was because the self-driving system was responding to a lot of spurious signals. It would often break for sort of shadows on the road and these sorts of things. And so to try and smooth the motion, there was a 1 second sort of delay to see if this was essentially effectively a false positive and whether the vehicle could continue. The safety driver that was in the vehicle was not alerted to that emergency being recognised. It's only after the 1 second action suppression that the safety driver was alerted that an emergency had been detected. So this was now 0.2 seconds prior to the collision, at which point the self-driving system wasn't actually even enabled to operate emergency braking. It was just assumed that in these instances that the human supervisor would step in, and that was their responsibility. The Volvo inbuilt safety systems were all deactivated on these vehicles, and it was determined later that if the standard Volvo systems had been functional, which just used sort of, I think, ultrasound and fairly basic technologies relatively, the collision would have been avoided, and the car itself would have come to an emergency stop. So that was essentially a very busy but a slide, a sort of complex accident sequence. Well, I think it's useful just to start exploring what does that mean for how we understand how to govern, how to manage, how to implement safe AI. And I'm going to use that as an example just to work through some of these in the next 5 minutes. Now, we know a huge amount about this event because the people that investigate things like this is the National Transportation Safety Board. They investigate 777s that crash at San Francisco, and also pay a lot of attention to whether bolts have fallen out of the side of a Boeing MAX 9. Also, sometimes look at the most serious or important or relevant vehicle road transport collisions. And so there was an enormous amount of scrutiny that went into this particular event. And in addition to commissioned investigations from the organisation themselves, and a lot of very, very in-depth journalistic investigation into the company and the events surrounding it. So I used all that data. Essentially, if any of you have ever used sort of qualitative methods, you sort of spend several months mainly locked in a dark room working through enormous corpus of data, trying to build out a coherent model of what was going on in that particular event, trying to track every single instance of text to every other, and to make sure that you can build a model which accounts for everything that has happened. So that's what I want to just say a few descriptive and hopefully helpful words about, which is what are the sorts of socio-technical patterns of risk that we need to think about avoiding when we implement and deploy AI in healthcare settings. Now, in this case, in the Uber vehicle, we've got a situation where there were this array of different patterns of risk, which not only were present in this event, but also I think have a lot of historical standing in the literature that we know about, that exists and it is out there already around other accidents and events. So I just want to very quickly describe some of these structural sources of risk, the organizational sources of risk, technological, epistemic, which is a fancy way of saying how does your system maintain knowledge of what it's doing, how do people understand what they're doing, and cultural processes. So I'll just pick up on a few of these points just to illustrate the examples. So to start with, there's enormous, essentially existential pressure and a race to deploy these sorts of systems. A race around whether there'd be future funding available to burning through finances very rapidly to try and deploy these very expensive, large-scale AI systems. That led to a considerable focus on performative production, this sense of managing to some external required standard, which in this case was autonomous miles driven on public roads, which was what everyone was competing against, which deflected attention from a lot of other performance indicators. There was also a lot of competitive secrecy that this drove, as it seems that there was reluctance to share safety data and potentially in some cases even compile safety data in case it damaged essentially the view of the external view of the safety of these systems. There was also a great deal of what could be described as learning lag, which is essentially running the system, operating the system far in advance of your capacity to actually learn from the events that are occurring. Compiled or connected with this was things that I describe as supervisory degradation. So a gradual reduction in the human supervision that was being deployed alongside the system, which of course fed into this learning lag because there were fewer people close to and supervising and monitoring the system. You experienced and catalogued fewer incidents. Ironically, the whole safety of the system was built on vigilance dependency. So essentially, it was the human operator who ultimately was responsible for checking and stepping in as soon as there was a problem. And it was just assumed, well, people presumably are perfect and never make mistakes and can be entirely relied upon to do that, which of course is sort of against much of what we know. But human vigilance was a very large part of the safety structure, and that was primarily allowed because there was a lot of presumptions of human reliability. I think driven by these what were documented as fairly considerable gaps in competency around safety management, and particularly the operational safety of running AI systems in complex public operational settings. So I'll just sort of move through some of this. There's papers out there that I've written that I can point to, but just to indicate there are also capability constraints built into the system, sensitivity smoothing to make the system operate in ways that performed the core function that people were worried about, i.e., having a smooth ride, as opposed to actually the safety of the system and the hazards that were being recognised. So I'll leave it there. But essentially, that all meant that as soon as a small disruption occurred with a pedestrian crossing the road, hard to classify, all of these failures, those failures cascaded very, very rapidly through the system. So just in the last minute, I'll leave you with just some implications for what this essentially might help us with as we think about safe deployment in healthcare. One is that we need to really understand and think about the socio-technical sources of risk. So what would do our systems, do our governance systems, do our monitoring systems really allow us to think about these socio-technical sources of risk that surround and support the immediate device and the interaction with the device and the algorithm and the technology, and doing some work trying to develop what might be diagnostic prompts to help think that through. Second is, what are the patterns of resilience which actually counteract the sort of countervailing forces against these sources of risk? And again, there's another paper out just a few months back looking at this in healthcare. What are the patterns of socio-technical resilience we might want to see and we might expect around AI systems and deployment? So, for example, translating this idea of from learning lag and operating the system too far ahead of your capacity to learn to actually deploying systems indexed to how much capacity you have to audit and analyze and learn from those systems. Likewise, building in structural disruption mitigators, so things like only using perhaps certain systems when you're dealing with conditions that have a very large diagnostic window and multiple contacts with the patient, rather than a very sort of small diagnostic window that when a patient then is sort of lost to follow-up or those sorts of situations. And then finally, I think there's still a very, very big question around what does a learning infrastructure need to look like to fully grapple with all of these sources of socio-technical risk and these socio-technical patterns that we will no doubt encounter in different ways in different settings in healthcare. So thank you very much.